Hey there, I'm Fritz, a PhD candidate from Hans-Peter Pfister's Visual Computing Group at Harvard University, where I work on scalable visual exploration systems for biomedical data. Today I'm going to present our work on a generic framework and library for exploring small multiples through interactive visual piling, which was a fantastic collaboration with Xinyi Zhu, Wei Chen, Niels Scalenborg, Benjamin Bach, and my advisor Hans-Peter Pfister. Also, I'm on the job market this fall, so if you or your school is looking for someone like me, I'd be super excited to chat. Small multiples are a widely used visualization technique to display complex datasets through a series of miniature visualizations that can show different dimensions, facets, or subsets of the dataset. Arranged in a grid, small multiples afford direct visual comparison and are applicable to a wide range of use cases. However, a major challenge with small multiples is scalability. For instance, on the left we see a large photo collection of cars in context. In the middle we have necklace sketches, and on the right we plot area charts of COVID-19 infection rates. But as you can see, with increasing number of small multiples, exploration and comparison become less effective due to the decreased availability of screen real estate per visualization or extensive navigation that is required for detailed inspection, and increased efforts for sequential scanning of individual items. Moreover, questions regarding multiple items become challenging to answer effectively. For instance, it's hard to estimate the total infection rate of 3 or more countries. To address these challenges, we can employ interactive piling. Inspired by the act of physically piling paper documents, visual piling describes an interface for interactive spatial grouping of small multiples into piles of partially overlapping items. Visually, a pile can consist of 3 types of element: the partially overlapping items that make up the pile, a cover item that is shown on top of the pile in its entirety, and a set of preview items that hint at the visual details of individual items. The cover and preview items are optional and can be used for alternative pile designs. For instance, on the left we replace the original items with one-dimensional previews that show the edge of the books. Now, to distinguish piling from other forms of spatially arranging small multiples, piles should adhere to the following 4 properties. First of all, as we've seen before, items that comprise a pile should occlude each other partially to form a single, mutually connected unit. Second, a pile must differentiate itself visually from a single item. Third, items on a pile should act as a single item during the exploration. And finally, piling should be seen as a dynamic process where the piling state can change frequently. In contrast to other aggregation techniques, the goal of piling is to compose and disperse piles interactively rather than to just consume a static grouping or aggregation state. But how should we go about designing a piling interface given many possible pile encodings, as we show here already? To answer this question, we systematically analyzed previous piling interfaces from the human-computer interaction and visualization community to identify common goals and tasks that apply across various different use cases. In HCI, piling has been studied as an interaction technique for organizing digital document collections in desktop environments. The primary takeaway is that piling is understood as a preferred approach for casual organization, as it's cognitively less demanding compared to traditional filing techniques that rely on folder structures. In visualization, piling has been used only in the context of matrix visualizations for comparison. On the right side you can see some examples from 3 visualization papers that employed piling to compare individual matrices. Now, based on this literature review, we defined the first generic design space for interactive visual piling. The design space is structured according to the following 5 high-level analytical tasks that we generalize from related work and that every piling interface should support, which are grouping, arrangement, previewing, browsing, and aggregation. For grouping, we distinguish between manual grouping, which is important for personal organization and comparison, and automatic grouping, which is often required for scalability and can be achieved via layout-driven, proximity-based, or similarity-based procedures. For arrangements, we consider the relative positioning of items on a pile and the absolute positioning of piles to each other, which can be used to encode additional information. For instance, the randomness of item arrangements can inform the user of their pile interaction frequency. To afford content awareness, piles can implement 5 different layout types for previewing items. The choice here depends on the visualization type and the application-specific tasks. For instance, partial and gallery previews are particularly useful for image data, while combining previews can be useful for scatter plots or line charts. In the context of piling, we regard browsing as the act of inspecting the visual details of individual piled-up items. To support efficiency and scalability, piling interfaces typically provide multiple browsing interactions, as I will show you in a minute. And finally, aggregation is the act of summarizing piled items into a concise form to enhance the content awareness of pile previews and aid comparison between groups of piles. Now, to increase the practical accessibility of this design space definition and enable rapid prototyping of new piling interfaces, we have developed a JavaScript-based library called Piling.js. We built Piling.js around a data-agnostic WebGL-based rendering pipeline and a declarative view specification to avoid having to write low-level code. To get started, we, as the visualization designer, need to provide the data, a matching renderer, and a view specification, while Piling.js manages the state and provides manual and automatic grouping, arrangement, and browsing interactions. For manual interaction, Piling.js implements common gestures like drag and drop, lassoing, or in-place and dispersive browsing that are useful across use cases. Piling.js also offers means to automatically arrange and group piles based on the item's underlying data, as you can see here. And now you might be wondering how exactly it's possible to render these matrix piles which feature one-dimensional previews on top of a cover item that is showing the mean of the grouped items. And so here's again the basic rendering pipeline from the previous slide. However, just a single renderer cannot show cover and preview elements that we've seen before. Therefore, Piling.js allows to optionally specify aggregator functions for the cover and preview renderings. Importantly, each part of the 3 rendering pipelines can be mixed and matched to support all types of pile encodings presented in our design space. Out of the box, Piling.js can render images, SVGs, and matrices as we've seen before. And it's also possible to develop your own custom renderer. For instance, in this example, we're showing multi-channel immunofluorescent microscopy data that is rendered with a custom WebGL program to provide smooth dynamic re-rendering. Now, to put this all together, I want to show you 2 examples how the piling metaphor enhances the exploration of small multiples. For the first example, we're coming back to the necklace sketches from the beginning. This dataset from Google QuickDraw is composed of thousands of sketches created by users around the world whose goal was to draw recognizable necklaces in under 20 seconds. Using visual piling, we want to identify and analyze clusters of recurring necklace concepts. Now we start by arranging the sketches according to a UMAP embedding to gain an overview of the entire dataset. The embedding here is placing similar sketches close to each other to highlight clusters within the dataset. To stratify this view, we can automatically pile up items that are located within the same grid cell, and then manually adjust the grouping using the built-in lasso tool. To summarize the piled-up sketches, we are showing an average as the pile cover, which enables us to quickly identify different concepts of a necklace. We can now further browse and compare these concepts by looking at piles in isolation and adjusting their arrangement. Visual piles also afford encoding related metadata. For instance, by visualizing the geographic distribution of the sketches as these stacked bar charts here, we can quickly see that in South Asia, an open beaded necklace is more commonly drawn than an open pendant necklace. In the second example, we're looking at scatter plots comparing countries by their fertility rate, shown on the x-axis, and life expectancy, shown on the y-axis, from 1960 to 2017. The data is stratified and colored by geographic region. Since the high number of scatter plots is pretty overwhelming, we group the different regions by year and then order them by decade. To more easily compare the worldwide development, from 1960 to 2017. We can now see that on average, the life expectancy increased while the fertility rate decreased. For a more targeted analysis, we start by dispersing all piles again and subsequently group them by geographic region. To gain an overview, we made the cover show a trace of the development over time, where brighter dots refer to more recent years. The rectangles next to a pile are so-called indicative previews that tell us which years and regions are represented on a pile. They also allow us to quickly leaf through the pile to inspect individual years in place. And finally, we can compare pairs of regions through manual grouping. In this example, we can see the remarkable catching up of countries in East Asia, shown here in blue, compared to the United States and Canada, which are shown in yellow. In total, we have evaluated visual piling with 8 different use cases, including examples from machine learning, immunofluorescent microscopy, genomics, public health, and geography. For details, please refer to our paper and explore the examples yourself online. In summary, visual piling is a generic, flexible, and useful approach for exploring any small multiple setup that would benefit from interactive reorganization and comparison of items. It's particularly useful for cluster and time series analysis. And we hope that our design space and the JavaScript library will enable others to create new piling interfaces for their specific use case. Thank you.